So I would like to welcome you all to our second live session for the Science and Progress series. My name is Amal Hamadi. My colleague Amna and I will be hosting these sessions through Monday through Wednesday, every week. We aim through this journey to take you in a kind of trip through the latest scientific research done in the UAE with exciting guests who are distinguished scientists and researchers from the UAE. They are also the members of the Mohammed bin Rashid Academy of Scientists. All have had great impact to their research in the scientific field, whether nationally or internationally. With that, I am very, very excited to welcome my guest today. She is the Director for Research and Innovation Center on CO2 and hydrogen, the Rich Center at Khalifa University. She's also a professor of chemical engineering and the editor-in-chief for the journal Molecular Liquids. Dr. Lourdes Vega is also this year's recipient for Mohammed bin Rashid Medal of Scientific Distinguishment. Welcome, Dr. Lourdes, and thank you for giving us your time for this session.
Thank you.
So I would like to start the session with a question I like to ask a lot of people I meet, is why did they decide to go into the field they are in, and how did they decide on doing that? So my question to you is, why did you decide to become a scientist?
That's an excellent question. I guess I decided that because of part of my character and part of what I like. So I was always interested in know what happens, but why things happen the way they happen. And in the end, I discovered this is science. So I discovered this when I was studying physics or biology or things like that. And then I said, well, can I really try to explain what happens? And if I can explain that, improve things so that I can, have an impact on the society and on our quality of life. And I mean, from math to this is a huge jump, but we will see later that that's actually what doing science is. So I am a scientist because I really want to understand and improve things around me.
So you're the director of the Rich Center, and you work in sustainability and CO2. Can you maybe explain to us what is sustainability and what does it mean to do research in this field?
Thank you. I first start to saying this Rich Center is not because we are rich because we have money. It's because we are rich in knowledge and in ideas. So this is what we want to do, focus on the specific area of clean energy and sustainability. So when we talk about CO2, for example, we can see CO2 as the bad guy because that's how it appears in the media. Very bad, a lot of CO2 into the atmosphere. Or we can also see the CO2 as the good guy because we can actually capture the CO2 and use it for different applications. And this all is related to fossil fuels that we use to produce energy. Can we also work in other sources of energy? So for example, hydrogen, which is a clean source of energy, is a vector of energy actually that can be used for different applications. So this is all we do in the Rich Center. So when you ask me about sustainability, what is sustainability? Sustainability means sustain, to hold, to maintain, okay? And this is what we want to do to keep our planet as good as it is or better. Doing what? Doing, for example, taking care of the quality of the air. The quality of the air, so I don't have contaminants going into the atmosphere. Taking care of the quality of the water, removing contaminants from water and having enough water. So water is not part of the Rich Center, but the materials we develop for CO2 capture can also be used for water treatment, for removal of contaminants. And the last part is the food that we eat. No? So if we have very good air, very good water, but we don't have food, then we cannot survive. So the food can be preserved also by using CO2, for example. So in the Rich Center, we work in all these areas.
Okay, so I know you have a presentation you want to talk about today about a lot of examples of research have been done during working in the Rich Center. Do you want to maybe share that, and then we can talk about what kind of research is done in sustainability?
Sure.
Yeah.
let's start. So the title of the presentation is from, let's see if it opens. Okay, so the title of the presentation is from lab to market and what makes research a successful story. I put a second title, which is why to work on sustainability. And this is what I want to talk about right now. So how do we go from having a wonderful idea that we have here on the left to trying to implement this in a lab, see what happens, if it works or it doesn't work, like this poor guy here, and if it works, how do I really move this to have like a better car, to even have the prop that we just sent to Mars, better medicines, a greener city, food. This is a little bit the idea of that, okay? So I have been working on this for many years, but it has been fine-tuned, let's say. It's not that at the beginning of my career, I thought I wanted to work in these areas. What I say is I wanted to apply, to learn more science and apply this to problems of relevance, okay? I mean, to have my small little contribution to that. So through 30 years, I have been working in academia and in industry, and I have been in the US, in Europe, and in the UAE, always with this idea of how can I help, okay? So areas, for example, in which I work right now as the CO2 capture and utilization we talk about hydrogen, but I also work on energy storage, on hydrogen production, on new refrigerants. What do all these things have in common? I mean, and I am a very dispersed person? No, let's talk about sustainability and let's talk about some of these examples. And then what do we need to do to be successful on implementing some of these ideas to the market, and overall, how to become a scientist. So I like to start always by defining things so that we know what we are talking about. So when we talk about sustainable products, we are talking actually about services and products that allow us to improve the quality of life, but without having a negative impact into the environment, while also being economically affordable. So, I mean, any company will work to make profits. That's the purpose of a company. So the idea of having this sustainability behind the profit is that we also take care of our planet. So here is the balance here. And then I always give the example that in order to do this, we have to think green, because it's possible to be very profitable while also being very sustainable. So we have to think green, and we need to take care of our planet, because this is the only planet we have, and this is the planet we have for the future generations. Then why do we talk about CO2? Why do we have to worry about CO2? So I have a small video here that talk about CO2, greenhouse gases, climate change, and sustainability. And I think it's good to put in perspective why are we working on sustainability?
Human activities, from pollution to overpopulation, are driving up the Earth's temperature and fundamentally changing the world around us. The main cause is a phenomenon known as the greenhouse effect. Gases in the atmosphere, such as water vapor, carbon dioxide, methane, nitrous oxide, and chlorofluorocarbons, let the sun's light in, but keep some of the heat from escaping, like the glass walls of a greenhouse. The more greenhouse gases in the atmosphere, the more heat gets trapped, strengthening the greenhouse effect and increasing the Earth's temperature. Human activities, like the burning of fossil fuels, have increased the amount of CO2 in the atmosphere by more than 1/3 since the Industrial Revolution. The rapid increase in greenhouse gases in the atmosphere has warmed the planet at an alarming rate. While Earth's climate has fluctuated in the past, atmospheric carbon dioxide hasn't reached today's levels in hundreds of thousands of years. Climate change has consequences for our oceans, our weather, our food sources, and our health. Ice sheets, such as Greenland and Antarctica, are melting. The extra water that was once held in glaciers causes sea levels to rise and spills out of the oceans, flooding coastal regions. Warmer temperatures also make weather more extreme. This means not only more intense major storms, floods, and heavy snowfall, but also longer and more frequent droughts. These changes in weather pose challenges. Growing crops becomes more difficult. The areas where plants and animals can live shift, and water supplies are diminished. In addition to creating new agricultural challenges, climate change can directly affect people's physical health. In urban areas, the warmer atmosphere creates an environment that traps and increases the amount of smog. This is because smog contains ozone particles, which increase rapidly at higher temperatures. Exposure to higher levels of smog can cause health problems such as asthma, heart disease, and lung cancer. While the rapid rate of climate change is caused by humans, humans are also the ones who can combat it. If we work to replace fossil fuels with renewable energy sources like solar and wind, which don't produce greenhouse gas emissions, we might still be able to prevent some of the worst effects of climate change.
So this is why we can work on climate change. We can try to avoid the CO2 emissions, and we can work on improving the quality of life. This is the plot that you saw before. So the CO2 into the atmosphere have been going up and down. Of course, it was fluctuating, but never had reached the level that we are reaching right now. And it's still increasing. And if we look at the CO2 emissions by fuel type, which is the plot that I put here on the right-hand side, you can see that essentially is coal, oil, and gas. So these are the ones that are producing millions, thousands of millions of tons of CO2 going into the atmosphere, or CO2 equivalent, okay? The other greenhouse gases that we just saw right now. So we are not going to stop producing energy, because the energy is what we need for the quality of life. What we need to work on is on having clean energy. So because we are talking in the UAE, I guess we are interested in what happened to our country. So here is what happens. We are also contributing to these greenhouse gases emissions and CO2 emissions. So I put here on the left-hand side the emissions that we have by the energy sources. So we have little coal, however, we have a lot of natural gas and oil, which are contributing to millions of tons of CO2 going into the atmosphere. If we look at the economic sectors in which this is happening, we can see that the transportation is already 20%. Of course, the industry and the electricity and heat producers. When we talk about heat producers, we also talk about air conditioning and cooling systems, okay? The country has taken the steps, and our government has defined the energy strategy in which 44% by 2050 should be clean energy, then gas, which is less intensive than coal and oil, and nuclear and clean coal, okay? So it is important that we continue using the fossil fuels that we have, which are our resources, but in a clean manner. So why do we have to act? I think in the video it was clear, no? It was clear, it says that we are the ones producing this, but it's also in our hands to avoid that and to work on having a better world. How? There are different ways. The policy, which is something the governments do, preserving the CO2 sinks that we already have. This is in the hands of everyone. Working on alternative sources of energy like wind and solar. Our countries live in solar, for example, in the world. Working on energy efficiency and energy saving. Capturing the CO2 before it goes into the atmosphere. This is what we call clean energy as well. Or working on sustainable processes and products with low global warming potential. Global warming potential is the amount of global warming that a gas or a compound has compared to CO2. So for how long, for 100 years, will last into the atmosphere. CO2 has a global warming potential of 1, okay? Any other has much higher global warming potential. For example, the refrigerants have thousands of global warming potential. So as I say, CO2 is not the only bad guy of the movie. We have to work on some of them. But then what do we mean by capturing the CO2? For example, this is a power plant in which you put a fossil fuel and air, and it produces energy, which is the one we use for everything in our life. But then from the chimney, you see the exhaust gas will go into the atmosphere, and that's where the CO2 goes. So what do? Do we have like a system to capture the CO2 from the air? We say that the concentration of CO2 in the air is a little bit above 400 ppms, but this is very, very diluted. This is parts per million. So it's actually very difficult to capture the CO2 from the air. difficult in terms that you require a very, very high adaptive system and also a lot of energy to separate that CO2 from the air. So we're actually, when we talk about CO2 capture, what we talk about is not allowing the CO2, see the right-hand side here, not allowing the CO2 going into the chimney, but putting that into a system. Here we have an absorbent that will capture the CO2, will absorb the CO2, remove the CO2 from the gas, carry the CO2 here, and then send the rest of the non-contaminant gases into the atmosphere. So this is doable because it's more concentrated. So for example, if you have a coal power plant, it will be 15% of the gas is CO2. If you have a natural gas power plant, it's around 5%. So it's still very low, but it's much higher concentrated than the one from the air. And how do we do this? We need to have technologies to capture the CO2 before going into the atmosphere. I want you to think of a sponge because that's actually what we do. So you need to have a material like a sponge where you have many pores inside. So you have a lot of surface in which the CO2 can go inside. So then it captures the CO2, means it absorbs the CO2. But of course, what do you do with that? Now you need to dissolve the CO2, recover your sponge, and then do this many times in a cycle. So the example I put here is water, and this hand is doing the pressure that we need to dissolve the water. This is what we do when we talk about CO2 capture technologies. So there are two different ways that are more mature to do this in the market. Absorption by aqueous amines. This is a liquid, so the CO2 gets inside the liquid, very attracted by the molecules, and then you need to dissolve that. Or we can also do this with solid adsorbents materials, like zeolites, MOF, or many other materials. Okay, so you capture the CO2, you separate the CO2, and now what do you do with the CO2 that you capture? This is actually what we are working on in the RIP Center. So we are working on different projects related to CO2 capture for advanced materials, for example, that will be better than the current materials that we have. Better means more attractive and less energy intensive, so that I can absorb better and also dissolve with less energy cost. Energy is associated to cost, so cheaper. And then we also work on the different processes, and we are working on novel materials. For example, right now we are developing a project with the International Energy Agency on finding the best solvents for that. But the example that I put here is a local example. So together with Dr. Mohammed Abu Sahara and his team, we are working on using developing activated carbons from date seeds here from the UAE, which are the ones you see here. So we treat them, we produce these activated carbons, and then we study in the lab and biomolecular simulations what will be the best conditions of treating this material from the date seeds to produce these activated carbons for CO2 capture, and then do the process design to optimize the conditions for separating the CO2 from the rest of the gases. So essentially what we do is we are working on either the absorbents or adsorbents. We try to understand what happens inside the systems and how they interact with the molecules or the materials in order to optimize them. I always say that we put here what we call our molecular classes. In essence, we have to develop models to do that. A model is a mathematical expression. The language of science is mathematics, okay? So what is this? This is a cat, okay? So that will be my activated carbon that I showed you before. What is this? This is also a cat, but this is a refined model of my cat. It has a lot of details. What is this? This is also a cat, but it's a very simple model of a cat. So when you do a mathematical model to interpret the reality, you can use a very broad, general model, like a very coarse-grained model, or you can do a detailed model. The detailed model will require more mathematics. This coarse-grained model will require less mathematics, but they all will require that you know, that you understand what you are trying to model in your system, okay? So I say that once you capture the CO2, what do you do with the CO2 that you capture? So in the UAE, we have a beautiful project in which the CO2 is captured from a steel factory and is treated. This is captured with the amines that I mentioned before. Is treated and then is used to recover the oil that we have in the wells, okay? That's called enhanced oil recovery. This is a very nice application. There are some other applications that we can use. For example, we can try to break the CO2 molecule by using sun and convert that into other products. We can use machine learning and modeling to develop these materials, or we can convert this CO2 into valuable products. In this concept of circular economy from waste to materials, for example, this is a project we did with Dr. Nahla Alamodi and the students actually on using the slag from the Emirates Steel Factory and convert this into aerated carbon materials that we are using for insulated materials for construction. This is a project that our undergraduate students did at Khalifa University, and they were the winners of the Think Science competition. We are also working, for example, on using the rejected brine from desalination and using that with CO2 for other materials. But there are many other projects we are working on in trying different ways of using the CO2 that we capture. There is no one solution. We have to work on different processes that will open the opportunity to different markets as well, but there is no way we can use all the CO2 that we capture. We need to do other sources of energy to have less CO2 going into the atmosphere. Is all about CO2? No, we are also working on other compounds. In the video, you show actually that there are other greenhouse gases. So I took as an example the refrigerants, okay? Refrigerants, why? Because can you imagine our life in the UAE without air conditioning right now, for example? But can you imagine our life without preserving the food that we use in the market? Can we think of many other systems in which we don't have refrigerants? That's impossible to think. So refrigeration changed our life. And the refrigeration, any refrigeration circuit will have a fluid, which is called the refrigerant. That is the one that does the work of transporting the heat from the cold to the heat, and then moving the heat in or out, okay? So, and actually this involves a change of state of the fluid. So the refrigerants actually started at the beginning of the 20th century, and the first refrigerants were very good, but very inefficient, or they were toxic, or they were flammable. So the research started to look for other materials that would be non-flammable, stable, not toxic. And this was very good when we came with the chlorofluorocarbons. You saw them in the video. These chlorofluorocarbons were very good for refrigeration, but horrible for the environment because they are the ones that produce the ozone hole in the ozone layer. So after that, the Montreal Protocol say no refrigerants that cause this hole into the ozone layer. So then they started to find other refrigerants, which are hydrofluorocarbons, no ozone depletion or other properties, but they have a very high global warming potential. So in 2016, the Kigali's amendment to the Montreal Protocol say, no, we have to work on low global warming potential. Okay, so what is the problem? I mean, this is a very serious scientific problem. If you look at the periodic chart of the elements, and we put here the wishing list that we have for the refrigerants, you will see that only the ones in yellow will fulfill the requirements for having these properties. However, when you try to combine this hydrogen, chlorine, and fluorine, there is always a problem. If you combine hydrogen with chlorine, then it will become toxic. If you combine hydrogen with fluorine, it will become flammable. And if you combine chlorine and fluorine, they will last in the atmosphere for a long time. So, I mean, how do we do this? There are no more elements in the periodic chart that we can use. So we need to find new molecules, and we need to try mixtures of these molecules to see if with the mixtures we can find something that will work. So this is a very, very nice research opportunity and also a business opportunity. Some companies already saw that. So DuPont, for example, they developed these 4th generation refrigerants that are called hydrofluoroolefins, which are replacing the 3rd generation refrigerants, the one that are high global warming potential. And they created a company just for that, okay? So they were very successful in implementing this for the cars. The new hydrofluoroolefins are good. However, they are not very good for air conditioning applications. For air conditioning applications, some air conditioning companies had found some. Here you have, for example, the ones that were used before, 10,000 global warming potential to 600 global warming potential, but it's still very high. So we really need to work on that. If I put the circles here, this is the refrigerants we had before in the systems. This is the global warming potential of the refrigerants we are using right now. This is one for CO2. So this is an area in which we have to work, okay? But there are many others, as I explained to you. Okay, so I have an idea. My idea is I'm going to combine these compounds and I'm going to work with them on a refrigeration air conditioner, okay? Or my idea is, oh, instead of the date seeds, why don't I use this waste that I have here and I can somehow work on them and convert this into useful materials for CO2 capture, which will be local, and then we will use to avoid the CO2 emissions into the UAE, okay? So what does the idea for the research development come from? From many different areas. So first you need to know the needs. I'm telling you right now, for example, that we need to develop new refrigerants. I don't know if you knew that before or not, but this is something we need. I mean, there is one clear idea right now. I think we all know we need a vaccine for the COVID-19, okay? So by reading, by active listening, we have to be ready to find these opportunities. Then we have to be creative. We have to think out of the box. So maybe this material is not good for this application, but it may be very good for this other application. We have to see the market trends. So we need to know what the market is asking for. What are the needs of the people? We need to look for the social drivers. For example, sustainability. People were never thinking of capturing CO2 before until this became a problem, okay? Or the needs. So in the UAE, we have a very hot weather in summer. So can we have materials for construction that are insulating so it doesn't allow the air conditioning inside to go outside or the heat from outside to come inside, for example. So that's something that we need. Okay, so now I have this very nice idea and I developed that in my lab. How can it go to the market? So there are some key requirements that any product or service need to have. First, it needs to be technically feasible. So that's where we need the research. We need science and technology. First, the idea, see how it works in the lab. Can I optimize this? It works, okay? So if it doesn't work, forget it. Then it should be economically viable. There are many beautiful ideas that remain in the lab because they are very, very expensive to accomplish. So when we work on the products, we have to think of the cheapest way to develop that. For example, these activated carbons from the date seeds. So we have this waste, we can use this waste for this application, for example. So whatever we develop should be better than whatever it is already in the market. Because if people have something that works, why should they change? So it should have some other advantages. We should see that it is actually attractive to the market because it's not only is better, but it's more, I don't know, fancy, greener. It should have some additional attractive. And of course, it should be developed at the right time in the right place. Otherwise, maybe it was too early to be developed and then people don't understand the needs of that. For example, would anyone be worried about having a vaccine for the COVID-19 5 years ago? No. Someone will come with this idea, no one will pay attention to that. So there is no point on investing more money at that time. Well, right now we are doing this, okay?
Maybe Dr. Lourdes, before you go, it would be good maybe to give us an example of something you worked on that kind of went through this process to maybe make it easier for people to understand like what kind of areas that made it successfully happen. Because I mean, working with research and understanding that the results are correct, but then moving it and making it a product to have that big impact is not easy. So maybe an example will be much more understandable.
Yes, I will give you one example that worked and one that didn't work. Is that okay? So the example that worked, for example, I was working on using CO2. I need to explain it. So I was working on using CO2 to preserve the food longer. This is what is called modified atmosphere packaging. And I explained that. Okay, we don't have much of this in the UAE, so that's an opportunity for the UAE actually. So the atmosphere has oxygen, nitrogen, argon, and some small proportions of other gases, okay? The problem is that the oxygen oxidizes the product. So when you expose your food to the atmosphere, it gets it deteriorates, okay? So this is an application in the market already, which is called modified atmosphere packaging, in which you put your fresh food, remove the oxygen and replace that by CO2. So you put an amount of CO2, which the properties of the CO2 for this food is first is good, it's non-toxic at all. We actually drink CO2 with Coca-Cola, for example, remember, or with carbonated water. So the CO2 is good for the body. It has a bactericide effect and a fungicide effect. That means it retards the growing of the fungi and also of the bacteria, okay? So it preserves the food longer for that. However, another application that you can use to preserve your food longer is to freeze them, okay? So the frozen food lasts longer, and then you have to defrost to eat that. So what we thought is, can we combine both? Can we combine freezing with modified atmosphere packaging to make the food, to preserve the food longer and with a better quality? And if so, in which order do we have to do this? So do I put first this modified atmosphere packaging and then I freeze my food? Or do I first have the food frozen, and when frozen, I inject this gas? So we did all these experiments in the lab. We needed to understand what is the process of the molecules in the food, and like the proteins, how are they affected by the way in which you freeze them, and how are they affected by the modified atmosphere packaging. So we did all these experiments in the lab. We patented the process, and this is in the market already. So this is something we did in Spain, not in the UAE. But it's an application. We came the idea, we had the question, we look at the market opportunities. People wanted to have the food lasting longer and with better taste. And that's what we had by combining this modified atmosphere packaging with freezing. So this is one example.
I feel like you talked so much about positively about CO2. I feel like it's a wasted resources now. I'm going to be like...
No, because to use the CO2, you first need to capture the CO2, remember. Okay, so I can give you an example in which it didn't work, and it's actually related to CO2 capture. So we have been working, remember that I say that we need to have clear advantages versus the one available in the market to be successful, okay? So we have been working on many materials that we try to replace the amines that are used in the market today. And although they work technically feasible, remember, they are technically feasible. So we did all the scientific development in the lab to capture the CO2 in a more efficient and cheaper way than what is done today. In the end, our materials were more expensive, so it was not economically viable. So there are many cases like this. Also for water treatment, we have been working on materials to remove the contaminants in water and different processes. And we thought we had a great idea of using this specific material, but in the end, it didn't remove the contaminants at the level that we wanted to remove them. So many of the things you tried in the lab, they don't go to the market. Most of them actually, because the market few products go into the market. But the reality is that in the process of developing these new products, you learn a lot and you can apply this knowledge for other things. So thinking out of the box again, you make and use, recycle your idea for another application.
I'm just wondering if, like, whenever you reach like that, the end phase where you decide if you want to go to the market, if it doesn't work out, what do you do after that? So do you try again? Do you just move to the next project?
This is a very good question. So I will use this slide here. And this is what happens. So by the way, one of the things of being a scientist is that you need to be very resilient, okay? You don't get disappointed if things don't work, because most of the things we try don't work. Not even going to the market, not even in the lab, okay? But that's the beauty of that. You have to try. Otherwise, imagine, no? You go to a lab, you have an idea, you try for 1 week, it works. Then things will be very easy. So things are not that easy. You really have to work hard, be open-minded, and be resistant to that. So here is what is defined scientifically as the valley of death. So you have these very nice ideas, then you have to work on them, you put a lot of effort and money, and then this is usually done in university, government labs, startup companies, big companies, small companies. So you start to develop your ideas, you may patent these ideas, and then all of a sudden, they don't go to the market. They don't go to the market because there is not an opportunity, it was very expensive, or it doesn't work as well as you thought it will work. So first, to come here, you need to have the right partners, okay? So this concept of open innovation means that you need to have people who are really interested in your products and want to put the money and the risk to do that. So scientists don't work, maybe they do, maybe they work isolated in their lab, but that's not how the products go to the market, okay? You really need to have, as I said, you need to be an active listener so that you can see, okay, so if what I'm doing here doesn't work for this, can it work for these other things? For example, we are working on graphene oxide that we thought it would be a very good material for water treatment, and it is, but we thought of for removing these contaminants. So it was not an application, but it was good for another application in water treatment. So once you have your material, your product, you can try to see, okay, maybe it doesn't work for this. Can it work for this? Can it work for this other thing? Talk to other people, talk to other scientists, talk to people in industry, listen to your people, listen to your parents, listen, watch on TV, what are people talking about? Maybe this is an opportunity for this. And by the way, maybe you just have to put your thing on the drawer and work on another thing until the opportunity comes. So as I say, a scientist has to be very resilient. We have to be working there, very, very patient, and then try to find the opportunity. And if things don't go into the market, it doesn't matter, because the body of knowledge grows, and this is part of the reason for doing science, so that the people knows things that work, things that don't work, and opportunities. That's why the scientists also publish in journals, okay? So that other people learn from what we do, and they can build on top of that. And that's how science advances as well.
Okay, so maybe my last question, since we are here, is, I mean, learning about this process, what do you think, or what does it take to be a scientist or researcher? What kind of competencies you need to have when you go into science and research?
Thank you. Okay, so first is, do I really want to be a scientist? Look at the photo I put here. Maybe some people think we are just crazy people. Do you really want people to look at you like crazy people? I mean, I always explain this anecdote. When I was going to my children to school and then getting them back from school, and I was explaining to the other mothers there, they say, oh, what do you do? And then I was explaining what I was doing. My God, they look at me and say, oh my God, you look normal. Like, you are not normal. We are normal. We are really normal people. So being a scientist first is, do I have to study hard? Yes, I have to study hard. But this is for anything in life. If you don't put effort, you don't succeed. But in the end, you will be very happy to do what you do. This is a photo of Fali Al-Najjar. He's one of our master's students working in the lab. And you can see he's very happy with what he's doing. By the way, he's working on these materials for cooling applications, okay? So first, do you have doubts, or are you scared of that? Like, will I arrive? Would I fail? Okay, there are doubts for everything, but just try, okay? Or you can say, well, but really no one in my family has been in a scientific career before, and my friends are doing something different. That's okay. You don't have to be like all of them. And if no one in the family did that, you can be the first one. Maybe my friends and my relatives think I am a nerd for doing science. We don't care. I think no one thinks that of the people we had launching the Hop probe 2 days ago. So no, we are normal people that we require to do what we have to do. So does it require sacrifice? Yes. Nothing is easy and nothing is granted for free. But there is a secret. You have to be well organized. So if you are well organized, you can study science, you can do research, you can do sport, you can go to movies, you can read. There are many things. You have to be very well organized. Again, not only for doing science, for other things. You need to have a support team. As I say, scientists are not alone, and many of the things we try fail. So you have to be ready to fail. But fail is a success if you learn from that, okay? The driver should be like what you do and do what you like. And in this order, okay? But I mean, I have nothing more to say with the great example that we have from the UA Mars mission, that the slogan is the impossible is possible. This is how we do science. The impossible is possible. So if you want me to give you some key notes on what do you have to do to be a scientist, is have this idea that you can help others and the future generations by the work that you do. It is very rewarding because you see you can use your brain and your time to prepare something that other people will use, starting from your family and the other people. So you have to be brave, because really you need courage to do that. You have to be smart. You have to be flexible. If something doesn't work, it doesn't matter. I can try to do this in another way. You have to be generous, because for sure it requires time. You have to be humble. Many things don't work. It doesn't matter. Some others will work. We don't know everything. I already said you have to be organized. You have to work hard. You have to love math. Mathematics is the language of science. So if I don't know how to speak, how will I communicate? So if I don't know math, how will I do science? It's impossible. Think big. We can do great things. The impossible is possible. Think green, so that when we develop this science, we contribute to the wellness of the country, of the planet, and of the future generations. And my advice overall is have fun with what you do. And remember my cats. Math is there, is part of the effort, and is part of the smartness to pick up the right model to root the right things. So these are my advices for all of you. Overall, have fun.
Yeah, thank you, Dr. Lourdes, on the great advice. I would go back with math. All those people come and ask us, our students will be like, where am I going to use this? Why do I need to understand this? But if you're going into science, math and physics is like number one in everything. So, okay, so maybe now we can go to, we have a few questions. So there's an anonymous question that says, he wants to become a scientist and he's studying chemistry. So if I want to work in renewable energy, is this the right major? What is your major? What should I be specialized in if I want to work on like sustainability and renewable energy?
This is an excellent question. I didn't say that. I actually study physics.
Yeah.
So I like mathematics. I studied physics because I could apply the mathematics in physics. And then I decided to do engineering, and I became an engineer by training. I've been in engineering 30 years. So chemistry is a great field to work on, because it gives you the right ingredients. So you will have the mathematics, which we say you need, and you will know about the molecules, and you will know how they interact. So it's a great field to work on renewable energies, for sure. For sure, it's the right choice. How do you move into working into renewable energies? It will come with time. So you have to decide what to do after you graduate in chemistry. So will you go for a PhD, in which area, with which people? You have to explore a little bit, but for sure, this is a very good area.
Okay, so I have a really good question here. It says, how can I know if there's a market opportunity for anything I'm working on?
You don't know.
Like, this is a very big question, but
no, this is a great question. Why? Yeah. Because you need to have market training. Yeah. Okay, and this is something we lack in scientific careers. Okay, so if you are really oriented to develop products, you need to take courses for that. Okay, so you have to learn the same as you have to learn mathematics. You have to learn marketing. Okay, so you need to learn a little bit few tools about this, and overall you have to work with a person who has this experience. Okay,
can you maybe elaborate, what do you mean by like market training? So what does that mean? Like, what do I need to know, or what do they do at courses?
Well, you know, there are people that study economics.
Yeah, okay.
That's what I mean. So if you don't want to study the whole career of the whole subject on economics, at least you can do an MBA, which is a master on business and administration, for example, or take some postgraduate courses on marketing. So I was teaching here in Spain, I was teaching a postgraduate course that it was called From U to B, from university to business. okay? And that was explaining people what are the steps. Usually you need to really talk to people who have succeeded in launching products to the market. Yes?
Okay, so let's see. What another question? There's a lot of thank yous.
Thanks to all for being here.
One question would be, if I am a scientist and I don't have that background in market research, can I maybe collaborate with someone else to transform my product into something ready in the market?
That's the way to do it. That's
Yeah.
the way to do it. That's what is called open innovation. So you get the best ideas from everyone and you work together. By the way, this is the way it's done in the industry. So any company who is developing a product has a team in which you have people from R&D, people from marketing, and people from commercialization, okay, together. And the way the products are developed is by gates, okay? So you have the idea, then the team together will explore the idea. So is this idea a good idea? Is there a market for this? Can we commercialize this? Okay, yes, then we go to the lab. Okay, once it works in the lab, you do again another study. Is the market ready for this? Okay, so that's the way things are. So yes, you need to be aligned with someone with knowledge on that part.
Okay, so there's a lot of questions they're moving around. Okay, so there's this question that says, do I need to have combined theoretical and experimental experience to be able to do products? I think that's a yes.
that's yes. That's an excellent question also, by the way.
Yeah.
Yes, you need to have both because you need to understand what is happening. Okay, so yes, you need to have both.
Okay. Okay. Okay, so there's a lot of people asking for your advice for young scientists or people who want to work in physics and math, but they're afraid to go into that field, but they're worried because they will be doing like teaching in school instead of actually being research. So what would you
this is really very nice. I felt that way, by the way. So when I first, I didn't answer this when you asked me, but the first time I decided to become a physicist actually was because when I was studying physics in the school, I thought that the physics was cool, but the professors were no good. You know, it's difficult to understand. So I want to be a professor to really teach that so that the students like it. That's what I thought. Then when I went to the university, I discovered that teaching is great and I love teaching, but doing research is great. So that's how I decided to become a researcher as well. I'm doing both, no? I'm teaching in the university, in Khalifa University, and also doing research. So to do research, there is a path. You have to do your PhD, okay? So you have to do your master, you have to do your PhD. If you do your PhD, there will be opportunities either in companies, in the university to continue doing research, or to start your own company, or in the government. Okay, there are agencies in the government that also do research. So when you are in school, you only see that, you know, you do this and then you teach because that's what you see. You only see people teaching, but there are many other opportunities coming.
Maybe this question kind of relates to that one. So they're asking to your advice, basically, how to make their research impactful, and is it enough for me to just do research, like just publications? Is that enough impact, or do I need to go to the market?
You have to decide yourself. So it depends very much on the type of research that you do, and it's part of your choice. Okay, so doing publications is what most of the scientists do. Well, I can give you an example how it works. I give you some numbers. I have more than 200 publications. I have 5 patents, and I have 5 products into the market. Okay, so this is how it works. Most of the things you can publish in very high impact journal or in other journal, and only few of them will really go into something that is marketable and something that goes into the final product.
Let's see.
What I could say, sorry, to finalize this,
Yeah.
is that, I mean, if from the research that you do, in addition to having papers, you see a product in the market, you feel more fulfilled, let's say, you know, because you really see you had a clear impact today, in addition to the future generations, which is what you have with the papers that you publish.
This question from Lena. She says, like, when I do my research, do I focus on transferring it to a market or focus on the research itself? And I feel like you need to do both. Focus on the research.
No. Okay, let's put it this way. It also depends at the stage in your career, okay? So when you start to do research, first thing you have to do is to learn how to do research and to do it properly, okay? And to understand and to reproduce the data and to understand what you're doing and to advance in the state of the art with respect to what other people did. That's the very first thing you have to do, okay? What I say is you have to keep an eye on the possibility of transferring part of this research. It's different if you work in a company, okay? So if you work in a company, the purpose of you doing research is to develop products to go to the market. But that's different. Not when you are in the university. When you are in the university, you are in the university doing essentially fundamental research. Some of each could be applied research.
Okay, so this question might be related to math, but he says, I'm curious, do scientists in your field required working on computer programming? So I guess that's how we do math nowadays, is by using programming.
Yes and no. You first need to, okay, so the computer will do whatever you tell the computer to do, okay? Yeah. So if you put the wrong math into the computer, you will get the wrong results. So first you have to know math, and then you have to know how to program, and then you need to know how to use the computer. So in the end, for some of the calculations, yes, you will use the computer, and in some cases you can even buy a commercial software, but you still need to understand the basic maths behind that.
Okay.
No avoidable. We have to study math.
Yes, yeah, I agree. I mean, math for science is the most important, and you need to enjoy it because math is fun. It's like a challenge you're trying to solve. I think we have a lot of more questions. Maybe I should pick up one more before we end the session. Let's see, something interesting.
I see so many numbers.
Yeah, yeah. Okay, so there's a student here that says, I am in grade 9 and I want to become a chemical engineer. Is it better to start a study from now? I'm very excited.
This is great. I mean, this is a great question. Great question. Yes, start from now. Yes. By the way, I study physics because I didn't know that chemical engineering was the application of physics. So it's a beautiful field, really. You can do many things if you become a chemical engineer. So start as soon as possible.
I think we only have a few minutes to go. Since we already kind of gave a lot of messaging to people, and I can see a lot of people here excited to actually work in the field of chemistry and physics and chemical engineering. And I think I see a lot of people who are interested in CO2 too. Yes. So maybe, let's see, one more question. So there's someone who asks, is the only opportunity for a PhD holder to be a professor? So I think you kind of touched on this a little bit. So what happens after you get your PhD if you want to become a researcher or scientist?
No. Okay, so if you have okay, let's put it the other way around.
Yes.
To be a professor in the university, you need to have a PhD. Okay, so this is mandatory. Yeah. But the only option to be after the PhD is not to be a professor, for sure. Okay, and we have many examples in the UAE as well. I mean, there are many PhDs in ADNOC, for example. So they are working on a company or in any of the other companies. So this is something you have to decide while you are doing the PhD. Okay, you have to decide if you are more oriented towards working for a company or a corporation, or if you prefer to start your own startup company, developing some of the ideas you had. In this case, you probably have to work with your professor because the ideas came not only from you, most probably also from the professor. And then you need to see how to implement that. Of course, you can work also for the administration, as I say before, but I understand you are asking about continue doing research. If you want to continue doing research, you can do that in a company or in a university.
Okay, so since we only have 4 minutes, I don't know, your final messages, Dr. Lourdes. What do you want to say to the young science enthusiasts who are watching us? What do you want them to be doing in the future? What should they focus on maybe today to be better scientists in the future?
Well, my first message is that you have to work hard. Okay, so this is important because nothing is granted for free. Okay, it's not that you get an award or you appear on TV just because you discover this material for CO2 capture that will change our life, or this vaccine that will change our life. You have to work hard, but it is rewarding. This is the point. It is rewarding, okay? Really very rewarding. I mean, I have a lot of fun with the work that I do, even though I don't sleep many nights, okay? So this is what you have to, this is in the end what you want. What do you want to use your brain and your time for? For something that is useful and you feel rewarded because of that. And be humble, that's the other thing. We fail many times, okay? So we don't quit the first time we fail. We don't. We just continue. That's it. So that's my message. And have fun.
Okay, so I would like to thank everyone who joined us today. Thank you for your questions and thank you for watching us. Also, thank you, Dr. Lourdes, for this exciting session. I feel like we need to do 3 more sessions just to cover sustainability, CO2 by itself. What else can we do in research? Hopefully, we'll try to send answers to all of the people who sent questions. Just give us a few days. We will also send you all the links of the session to continue watching. Again, thank you all for joining us. Thank you, Dr. Lourdes. And I hope you enjoy this.
Thanks to all of you. Thank you. Thanks for the questions, for the invitation, and thanks for attending.